Hello, everybody. I hope you're all doing well. So, today we're going to be talking about a brief introduction to the study of mechanical vibrations. Okay, my plan for today is to look at an overview of mechanical vibrations, and then we will also introduce ourselves to certain idealized elements, which are springs and dampers, in a more formal manner. All right. All right, so for us, the plan for today is an overview, and then we will look at some idealized elements, such as springs and dampers. Okay, and then in springs and dampers, we look at fundamental laws that are used to model them. Okay, so we will look at fundamental laws to model them. All right. So first of all, an introduction or an overview. Okay. Let's go to the introduction part first. I'm sure all of you have heard of the word mechanical vibrations, right? Mechanical vibrations, they refer to the dynamic behavior or oscillations of mechanical systems about certain points, which are called as equilibrium points. Okay, so that's the first thing I want to write. So mechanical vibrations refer to the dynamic behavior of mechanical systems about certain equilibrium points. Okay. Okay, this dynamic behavior is typically also called as oscillatory or vibratory motion. Okay, so in this case, the dynamic behavior that we are interested in studying is the oscillatory motion. All right. And as you know, there is good vibrations, there is bad vibrations, right? So typically, good vibrations, example of desirable vibrations is music, something that we really love listening to, something that calms us down, and so on. Okay, in the form of sound vibrations, and then you have undesirable vibrations in the form of noise. This could also be the shaking of machines, or this could be the chatter of machine tools. This typically can waste energy. Okay, so we can have desirable and undesirable vibrations. Can be desirable in the form of music. Okay, they can be undesirable. This is typically in the form of shaking or chatter of machine tools. Okay, this undesirable form of vibrations which will result in loss of energy, okay, or waste of energy. All right. And so the question comes, okay, why do we need to study vibrations of mechanical systems? And in a sense, what is a mechanical system? That's something that I haven't defined. Let me do that as well. Mechanical systems, they can be defined as a combination of simple elements or complex elements that are used to realize useful action. Okay, so this is nothing but a combination of simple and complex elements to realize some useful action. Right, your automobile is a mechanical system. You have a complicated array of things that are connected together to realize a useful action, which is in the form of motion. Right now, so why do we need to study the vibrations of mechanical systems? Is we want to understand the behavior of these systems, and we want to design practical devices that enhance our lives. Okay, so why study vibrations? Right, we want to design, we want to understand the oscillatory behavior of mechanical systems. Behavior of mechanical systems. And this will enable us to design practical devices that enhance our lives. Okay, so that we can design practical devices that enhance daily life. Alright, so this is the reason for studying mechanical vibrations in that sense, and I'm just going to underline some terms that we are looking at here. Okay, mechanical systems and why study vibrations. Alright, then what happens is that typically, as you realize, mechanical systems are very complicated, right? So in order to reduce the mathematical burden of looking at complicated things, we try to model mechanical systems using certain idealized elements such as springs and dampers. Okay, it makes it more mathematically tractable to study these complicated systems. Okay, so in order to make it, since mechanical systems are made of complex arrays of elements, okay, arrays of parts or elements, okay, we simplify the situation by modeling such complex parts using ideal elements, okay, or idealized such as springs and dampers. All right, just want to write this word again here, and you will see that this is typically the foundational way of modeling things in mechanical systems. Okay, so we simplify. Okay, and this makes it more mathematically tractable. Okay, so this makes this more mathematically tractable. I did not mention that it makes it mathematically easy. It just makes it a slightly less difficult to handle complicated things. Okay, all right. And typically, to understand the dynamic behavior, we also make use of Newton laws and Newton-Euler equations. Okay, the mathematical modeling model is obtained by using Newton's laws, and if you have rigid bodies, then you'd be using the Newton-Euler laws as well. Okay, Newton-Euler equations. Okay, this is our typical aim, and in dynamics, in the course that you're studying right now, your aim is to come up with a mathematical model. Okay, the next step is typically you have to solve the mathematical model. The mathematical model will end up giving you the equation of motion. Okay, so this gives us the equation of motion. Okay, and then I guess if you want to look at the basic steps in the analysis, which we will not be doing, but something that you should be aware of, is that so let's say the basic steps in the analysis is to first of all model mechanical systems using these springs and dampers. Okay, so model of a complex system using idealized elements. Okay, then you come up with the governing equation or the equation of motion. This is like the physical model. Okay, you take a very complex mechanical system, you reduce it to a set of springs and dampers and masses. Okay, then you come up with a mathematical model. Which is going to typically be the equation of motion. Then you solve the equation of motion. Okay, there are several ways of solving this depending on whether the system is linear or non-linear. Okay, if the system is linear, then you can solve this using concepts of Laplace transforms, for example. Okay, you can also use basic tools of differential equation like methods of undetermined coefficient. Okay, undetermined coefficients. Okay, so these are typical ways of solving the equation of motion. Once you solve the equation of motion, you analyze the results. Okay, this can tell you about the behavior of the system. This can tell about the stability of the system. Okay, so perhaps you can also want to call this a stability analysis. Okay, and then once you analyze the results, then you can redesign the system. Okay, redesign for better performance. All right. So these are the typical steps that are taken in the study of mechanical vibrations of bodies. In our course, we will be limiting ourselves to the first two steps. Okay, we take a model of a physical system in the form of springs and dampers and masses, and then we come up with the equation of motion. Okay, all right. Now let us look at some idealized elements that are used to model the complex parts or elements of a mechanical system. Okay, so let us look at idealized elements. And of course, the first element that we're going to be looking at is the spring element. Okay, so first is springs. And I have to mention that these are linear springs. Linear springs. Okay, this is the first thing. Now, the very nice thing is that any body that undergoes elastic deformations can be modeled as springs, okay, or linear springs. So any body that undergoes elastic deformation can be modeled as springs. And typically you find this in your ballpoint pens in your hand as you're writing, or you can find this in the mattresses that you're sleeping on. This is so common, so ubiquitous, right? What do springs do typically? The springs, and maybe I should just write an example. So some pen, mattresses, and so on. And of course, if you go and look at the suspension system of an automobile, then you're going to have a complicated array of springs sitting out there, right? So that's a much more complex situation that I'm looking at. I'm looking at simple things as well in this case. Okay. Springs typically store potential energy when deformed, and this energy, you recover this energy when the springs retract back to their original position. Okay, so springs store potential energy when deformed. Okay, this energy is recovered or restored when the spring retracts back to its original position. Okay, so this is restored or recovered when the spring retracts back to its original position. All right. So this is a typical basic behavior of ideal springs. Okay, and how do we model springs? We model springs using Hooke's law. Okay, so Hooke's law is used to model the behavior of linear elastic springs. Right, this is typically the type of spring that we are looking at. Okay, and according to Hooke's law, and I just want to underline this. Okay, and typically the first thing as well here, any body that undergoes elastic deformation can be modeled as a spring. This is a very powerful statement because you can think of beams as springs. Okay, they're going to have a certain amount of stiffness. This stiffness can be used in terms of storing potential energy, and that is typically how one tries to model complicated beams in machines and so on. Okay, all right. So Hooke's law, I'm going to state this in the following manner. So the force of restoring force of the spring, which I'm going to call as Fs. Okay. I'm going to call this as F suffix S. Okay, I'm going to call the stiffness of the spring as K. Okay, and typically the units of K will be in Newton per meter or force per length. Okay, and then I'm going to look at the net deflection of the spring, and I'm going to call this as delta x. Okay, and according to Hooke's law, the restoring force of the spring is directly proportional to delta x, or Fs is equal to K times delta x. Okay, and so we need to define what is meant by delta x. Okay, so delta x is defined as the difference between, this is the net deflection of the spring. Okay, so this is defined as the difference between the displacement of the springs at either ends from its undeformed position. Okay, so this is the net difference. Let me not put the bracket. So this is the difference between the displacement of either ends of the spring from what I'm going to call as a static equilibrium position. Okay, look at this word. This is an important word here. Okay, static equilibrium position. That's supposed to be a C. So static equilibrium position, which is called as SEP. Okay, this is the position when the spring is unstretched. Okay, this is called as the unstretched position of the spring. This is the position when the spring is unstretched, which implies that delta of x at the static equilibrium position has to be 0. Okay, so which implies that delta x at the static equilibrium position is always 0. Okay, this is something that you want to always remember. Okay, and so this is typically how we model springs using Hooke's law, and the stiffness of the spring refers to the force required to cause a unit deflection in the spring. Okay, so if you want to think of it this way, the stiffness K okay, this refers to, or this denotes the force required to cause a unit deflection in the spring. Okay, and the stiffness is always a positive value. Okay, this does not change signs or anything of that sort, and these are all typically stiffness. You can think of it as a material property as well. Okay, and I just want to very quickly and very briefly draw this spring and show you all these things. Okay, so in this situation, I'm just going to start off by looking at a wall. Okay, I'm going to draw a very simple situation where I have a spring. Okay, and here is the spring. I'm first going to draw the spring at its unstretched position. Okay, alright, so here is the spring at its unstretched position, which means that the length of the spring at this position is called as the unstretched length. Okay, at this point, this spring is in static equilibrium, if you think of it this way. Okay, that's why it's called as the SEP of the spring. Okay, so this is, let me call this length as length L naught. Okay, the stiffness of the spring is K. Okay, and typically, let's say that I have some kind of a massless link that is attached at the end of the spring. Okay, this is a massless link, and later on we'll be adding masses and looking at motion and so on. Okay, so this is an example of a massless link. Some kind of a massless bar. Okay, and this position of the spring, I'm going to call it as the static equilibrium position when the spring length is unstretched. Okay, so L naught is unstretched length, and when the spring is unstretched, we know that it's at SEP, and I always want to have some kind of a sign convention, okay, to denote SEP, and here is what I'm doing. Okay, so look at this. I'm going to say that, okay, this is my sign convention. Things going to the right are going to be positive, and I'm going to call this as the coordinate x. Okay, and the coordinate x, if you see, it has a vertical line and it has a horizontal arrow. Okay, the vertical line denotes that this is the origin of the massless link. This is when everything is unstretched, and the arrow denotes that if the massless link is displaced in that particular direction, then the displacement of the spring is going to be positive for that particular end of the spring. Okay, so I'm just going to write these things down, but before that I want to show you at some point where the massless link is stretched. Okay, so let's see. So I start off with the same wall. Okay, now I'm looking at the spring that is a little more stretched than before. Okay, forgive me if it doesn't look too much like a spring. Okay, so now the spring is stretched. This massless link has now come to this particular position here. Okay, so this is the displacement of the massless link, and this displacement is pointing to the right, which means that it will be assigned a positive value in that case. Okay, and in this situation, the length of the spring, I'm going to call it as L. Okay, this is now the stretched length of the spring. This is L. The stiffness of the spring is still the same. Okay, and in this case, the length L is the stretched length. Okay, and so this sign convention, I just want to make a very brief note on it. Okay, so this coordinate x let me maybe write the title for this section as sign convention. Okay. This is very important because we need to know, even though this is completely arbitrary, what is positive, what is negative is arbitrary, we need to have a certain semblance of what we think is going to be positive versus negative. Okay. So from the perspective of sign convention, the coordinate x that you're seeing, that you're typically seeing, okay, this describes the position of the massless link. Okay, the positive sign convention is that the vertical line on this thing that you're seeing there, the vertical line on what I'm going to show here, okay, that vertical line, okay, represents the origin, okay, of the link when the spring is at SEP okay, and the arrow shows the direction of positive displacement. Shows the direction of positive displacement. Okay, and you can obviously see that if you draw the free body diagram of the spring and the free body diagram of the link, everything will be in static equilibrium. Maybe I can do that very quickly as well, okay, just to ensure that everything has been covered in this particular section. So if I look at the free body diagram, then here is what I end up getting. So at the stretched position, I'm going to take the spring and then copy that and paste that down here. Okay, so at the stretched position, this is the situation. I'm going to take the link and then I'm going to draw that right down here. Okay, now I'm going to have a force acting at either ends of the spring, right? This is going to be calling this the restoring force. Okay, so this is Fs, and this is also going to be the same force, Fs. Okay, the link is going to have equal and opposite force acting on it. Okay, and what I'm saying is that the link is being pulled by a force. Obviously, as I'm displacing the link, I'm applying a force F. Okay, so this is an applied force. Okay, and the displacement of that end of the link is x, and if the displacement is in the direction shown, then it's supposed to be a positive displacement. Okay, so in this situation, since it's in static equilibrium, this is F, and then the other force is going to be F suffix S. Okay, so that's the same force Fs, and so you can see that F is equal to Fs in this case. So F is equal to Fs, and this is going to be K times the displacement x. Okay, K times delta x, and delta x is in this case going to be x minus 0. Okay, because one end of the link is pulled by a distance x, the other end is not pulled at all, it's attached to the wall. Okay, so that I have delta x is x minus 0. Okay, so in this case, let me write this as delta x is going to be plus x minus 0, which is going to be x, which implies that F is equal to Fs is equal to K times x. Okay, so this is the sign convention that I'm talking about. All right. So this is a brief idea of springs, and you've seen this before earlier in other classes and so on, I'm pretty sure. Okay. Then I look at what are called as damping elements. Okay, so I had labeled this as A. Then I call what are called as damping elements. Or what are called as dampers. Okay, now typically we always want to think, okay, what is the need for having a damping element? Okay, damping elements are typically used to model parasitic losses in mechanical systems. Okay, so these are used to model parasitic losses in mechanical systems. Okay. Now dampers, what do? They exert a restoring force as well, but this force is proportional to the relative velocity between the ends of the damping element. Okay, I'm just going to write this is a mouthful of words. Dampers exert a restoring force, which I'm going to call as F suffix D. This restoring force of the damper is proportional to the relative velocity between the ends of the dampers. Okay. Okay, so in this case, we can say that the following, so this is the elemental law or the fundamental law. Okay, so law or the fundamental law that is used for dampers is that the damping force Fd is proportional to what I call as typically delta x dot. Okay, or I can say that Fd is equal to some c times delta x dot. Okay, where c is a constant of proportionality. Okay, and typically c is also called as the damping constant. Okay, in this case, so c is also called damping constant. And very quickly, before I go ahead and do that, the stiffness of the spring as units of force per meter or force per length. Okay, so K has units of force per length. Okay, typically newtons per meter or pounds per inches and so on. What are the units for the damping constant? And we can very quickly see this. The units for C, that's going to be force divided by velocity. Okay, so this is going to be Newton seconds per meter. Okay, so force divided by velocity, or typically Newton seconds per meter, or pound seconds per feet or pound seconds per inch, depending on what unit that you're using. Okay, so I'm just going to leave it at that. Okay, so now the other thing is when the system is at SEP, when all the springs are unstretched. Okay, so at SEP, dampers do not exhibit any restoring force, because dampers exert a restoring force only when there is a relative velocity. At SEP, what is the velocity? 0, right? So at SEP, dampers do not exert a restoring force. All right. And typically, where do you find these kinds of damping elements? You can find them in pneumatic door closers. You can find them in the suspension system of automobiles and so on. Typically, the one that you might have come across very often is this kind of a piston cylinder arrangement that is used in door jambs and so on. Okay, door closers and so on. So you can come across them across dampers in pneumatic door closers and suspension system of automobiles. Etc. Okay, and dampers do not possess any elasticity. Okay, dampers do not possess elasticity. And in that sense, both the springs and dampers are both considered idealized, because in reality, you see that a damping element is going to have its own mass. But we are using an idealized element, and the meaning of the idealized element is that the springs and dampers do not have their own masses. They are considered massless. Okay, so this is the first thing I'm going to go back and write down here when we talk about idealized elements. Okay, so the springs and dampers are massless. Okay. Are considered massless. This is very important, because in reality, if you're looking at a physical spring or a physical damper, those will considerably have a mass of their own, okay, which has to be included as a part of the mass of the system. But in an idealized situation, we are not going to be doing that. Okay. Then I want to draw the damping element or the damper very quickly, and then after this we will be done with this particular introduction, and then we will go on to do other more mathematically relevant things for us. Okay. So they have negligible mass, massless meaning negligible mass. That's something I want to mention. Okay, so this implies that negligible mass okay. Now let's consider a damping element at its initial position, where it is sitting undisturbed. Okay, this is the typical representation of a damping element. This is called as a translational damping element. You will also have what is called as a rotational damping element, similar to what you will have as rotational springs. We will not be looking at that in this particular course. But typically when you take system dynamics, that's something that one will be looking at. Okay, so I'm going to look at translational dampers. So this is the typical representation. It's going to have some sort of a cup and a cone, if you want to think of it this way. Okay, and this, in a sense, it represents the presence of a piston cylinder arrangement. Okay, and I'm drawing it at its SEP first, and I'm going to say that there is a massless link which is sitting at the other end here. Okay, let's give it some thickness. Okay, then this damping constant is typically called as C, and at this position the damping element is undisturbed or unstretched. Okay, so this is at SEP. Now from SEP I apply a force on the link, which will pull the link either to the right or to the left of SEP. Here is my sign convention. I'm going to follow the same sign convention as before, but this time I'm going to have a velocity on the damping element, right? Because I have to have a velocity on the link. This is once again a massless link. Okay, this is my sign convention. I'm going to start from SEP, or static equilibrium position. Now I take this link and then I apply a force on this link. What's going to happen is that it's going to be deflected onto the other side, and as it gets deflected, okay, this is typically what you'll be seeing here. Of course, this damping element is going to now produce a restoring force onto the link. Okay, and I'm just going to draw this here. So the link has now been deflected by means of a force that is applied on the link, and because of that is also imparted a certain velocity. Okay, and let's say that there is a force which is acting on the link here this way. So this is the force that is applied. This is the applied force, and this is still the damping constant C. And if I draw the free body diagram of the damping element, then all we know is that it's going to exert a restoring force on either ends. I'm just going to copy that and paste that here, and this is going to be equal and opposite to the force on the link. Okay, let's draw that here. And if I draw the damping force, this is the restoring force. This is F suffix D and F suffix D, and of course it's going to be equal and opposite to the force that is applied here. This is also F suffix D, and the other force is F, and you can automatically see that one end of the damper is connected to the wall, so there is no velocity at that end. The other end is connected to the massless link, which is displaced with a certain velocity of x dot, which means that the total relative velocity between the two ends of the dampers, okay, so if I write this way, so delta x dot is going to be plus x dot minus 0. Plus x dot because I'm seeing the link displaced to the right. And that's a positive sign convention, is that if things are displaced to the right, they will be treated as a positive quantity. The other end of the damping element has 0 velocity, which means that the damping force Fd is now going to be equal to c times x dot. Okay, this is typically what you see here. All right. And this can be used in more mathematically complex situations, which we are going to be using in solving certain problems. Okay, so that's the end of the brief section on introduction to mechanical vibrations and idealized elements. And I want to very briefly go back and look at a quick summary of what we did. So we started off with an introduction. Okay, we talk about mechanical vibrations as the oscillatory behavior of mechanical systems. It's important for us to study it because it's very practically useful, enhances the quality of life, and also curiosity, right? I mean, we study most things because we are curious about its existence, or we are curious about bringing out something, and we want to add on to that thought process by looking at certain things in certain ways. Okay. Vibrations can be desirable or undesirable, as you can see, and typically we use idealized elements to model the complicated parts of a mechanical system. This is mostly done so as to make it mathematically more easier to attack the analysis of the system. Okay, there are many situations where we will have to revert back to complicated aspects of the mechanical systems, but we will cross that bridge when we get there. Typical steps that you use is you model the system by making use of idealized elements and so on. Then you come up with a mathematical model of the system which gives you the equation of motion. You solve the equation of motion, you analyze the results, and then you go back to redesigning it for better performance if necessary. Idealized elements, why are they called idealized, is because they are considered massless. Okay, then you have springs which typically follow Hooke's law. According to Hooke's law, spring force is proportional to the net deflection of the spring. The net deflection of the spring is the difference between the displacement of the two ends of the springs. We define what is called a static equilibrium position. This is the position when the spring is completely unstretched. Okay, and then we showed these figures and so on. There is a sign convention that I use here. I want to dwell on this a little bit. The sign convention says that the vertical line that you see on here, okay, that's considered the origin, which means that the system is at the static equilibrium position at that point or at that location, physical location. Then the positive sign convention says that if this link here, as you can see, is displaced to the right, then it's going to be given a positive displacement value. If the link is displaced to the left, it's going to be given a negative displacement value. And depending on whether the link is displaced to the right or the left, the spring is going to be either in tension or in compression. All right, and then we go to the damping element, where the damping element, we say that the restoring force of the damping element is proportional to the relative velocity between its ends. And in this case, we start off at ACP. The link is displaced by applied force, so it has a velocity as well in the same direction. It's a massless link, of course. Then we say that, okay, if I draw the free body diagram of the damping element and the free body diagram of the link, you see that everything is in balance because you're now still looking at it from a static perspective. Okay, and so we see that F damping element is C times X dot. All right. So I hope this was useful to all of you. We will be using this to go on to single degree of freedom and multi-degree of freedom systems in the next lecture. All right. Thank you very much, and take care of yourselves. Bye-bye.